Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from CUHK Lab Vision-DeepResearch, Incentivizing Deep Research Capability in Multimodal Large Language Models. Multimodal large language models have become very capable at understanding images and text, but they still struggle when a question depends on detailed, up-to-date facts from the real world. Recent systems try to fix this by letting models reason, then call tools like web search. That helps, but today's multimodal agents usually search in a very shallow way. They assume a single image query or a couple of text queries will magically retrieve the right evidence. On the real web, with cluttered images and noisy search results, that assumption breaks down. Many queries just miss the target entirely. The authors highlight two core problems. First is the hit rate problem. If you send a whole image to an image search engine, the result is often dominated by background clutter instead of the object you care about. Even if you crop around the right entity, different crop sizes can lead to very different search results. Second, current agents rarely explore deeply. They make only a handful of tool calls, then stop, even when the evidence is incomplete. That shallow behavior is not enough for complex, multi-hop questions that require piecing together information from many pages and images. Vision-DeepResearch is proposed as a new paradigm for multimodal deep research. Instead of treating search as a one-shot operation, the model performs many rounds of reasoning and tool use. It searches over multiple entities in the image, at multiple spatial scales, and combines that with multi-hop text search. The system is designed to support long trajectories with dozens of reasoning steps and potentially hundreds of search engine interactions, all coordinated inside a single multimodal model. To make this work, the authors build a highly automated data pipeline. They first synthesize high-quality factual visual question-answering examples, and then generate long, multi-tool trajectories that solve those questions. These trajectories teach the model how to plan, when to crop images, when to search, and how to integrate evidence. Finally, they train a base multimodal model with a mix of supervised fine-tuning on these trajectories and reinforcement learning in a real online environment. The result is an end-to-end agent that can independently plan, search, and answer complex multimodal questions. The design is grounded in how humans actually search. Real web images contain many objects, varied scales, and messy backgrounds. Search engines can behave unpredictably, even for very similar queries. Humans cope by iteratively refining their search. They zoom in on different regions, try alternative keywords, and keep going until the evidence is convincing. The authors argue that multimodal agents should behave the same way. That means optimizing for long horizon behavior, not just 3 to 5 tool calls, and explicitly modeling search as a trial and error process. The first major component is multi-entity, multi-scale visual search. Given an image and a question, the model first reasons about what might be relevant, then proposes multiple bounding boxes over the image, including fine-grained entity-level regions. Each crop, at different scales, is sent to a visual search tool that returns candidate web pages. A website visit tool fetches the page content, and an auxiliary model summarizes and filters it, keeping only the evidence that truly matches the cropped region. Over multiple steps, this builds up a pool of visual evidence grounded in specific entities and scales. To avoid either stopping too early or searching forever, the pipeline uses a separate judge model. At each stage, this judge looks at the original image, the question, the accumulated visual evidence, and the ground truth answer. It decides whether the current evidence is likely sufficient to support downstream reasoning. If not, the system continues to generate new crops and search actions. If yes, it stops the visual search phase. This simple hit signal lets the pipeline adaptively control how deep it searches for each question. The second component bridges from visual search to powerful text-only deep research models. After collecting visual evidence, the system generates a detailed textual description of the original image. It then replaces the image with this description in the trajectory, while keeping the reasoning steps, tool calls, and observations intact. This transformed context is fed into a text-based deep research foundation model, which continues the trajectory using web search, page visits, summaries, and even Python tools. In this way, long-horizon text-only deep research capabilities are transferred into the multimodal setting. By combining the visual and text-based segments, the authors obtain full multimodal deep research trajectories. Starting from an image in question, moving through multi-scale cropping and visual search, then continuing with text-only deep research until an answer is produced. They then apply rejection sampling. An LLM checks whether the final answer matches the ground truth. Only consistent trajectories are kept for training. In parallel, they also generate text-only deep research trajectories for the same questions, giving the model additional supervision on long-horizon tool use. A key ingredient is a high-quality factual VQA dataset. The authors start from multiple open-source image collections, focusing on complex real-world scenes with many entities. They filter out small or trivial images using an MLLM as a selector. Then they apply two strong filters. If a powerful MLLM can answer the question without external evidence, the sample is discarded. And if a simple full-image search already retrieves perfect evidence, it is also discarded. What remains are genuinely challenging, fact-intensive VQA problems that require robust search and reasoning. To push difficulty further, the authors synthesize what they call fuzzy multi-hop VQA. They begin with entity-level questions tied to specific image crops, like asking for the name of a person or object. Then they obfuscate the answer by chaining relations around it. For example, asking about the teacher of the cat owner's daughter instead of directly asking for the cat's name. They also obfuscate entities by following links across web pages, replacing the original entity with related ones. This interleaved obfuscation forces the model to perform multi-hop reasoning across both visual and textual evidence. The question synthesis process is designed to mimic how humans write good exam questions. For each entity, an MLLM extracts keywords and queries external sources to gather more context. Another MLLM then proposes multiple candidate questions based on different pieces of retrieved evidence. A judge model evaluates these candidates and selects the most reasonable, objective one. This loop is repeated as answer and entity obfuscation proceeds, gradually building complex, realistic multi-hop questions paired with precise answers. Training starts with supervised fine-tuning. The authors collect about 30,000 high-quality multimodal deep research trajectories. These include verified fact-centric VQA problems, text-only QA problems with deep research trajectories, and fuzzy multi-hop VQA instances. The model is trained auto-regressively on the full trajectories, including the internal reasoning, the tool calls, and the final answers. This stage teaches the model the basic behaviors of a multimodal deep research agent, how to plan over many turns, how to crop in search images, and how to integrate visual and textual evidence. After supervised training, the model is further refined with reinforcement learning. Using 15,000 challenging VQA instances, the agent interacts with a real online environment that includes visual search, text search, and web browsing. Trajectories can be up to 50 turns long with large context windows. The optimization uses a group relative policy optimization method, and rewards are provided by an LLM judge that checks whether the final answer is correct. This RL phase encourages the model to discover more effective long-horizon strategies than those seen in the offline data. Long-horizon RL with tool-using agents is technically challenging. The authors design a high-throughput, asynchronous rollout system that can handle many tool calls in parallel, including multiple image crops in a single step. They detect and cut off degenerate behaviors, such as repetitive text loops or repeated tool call errors, to avoid wasting time on hopeless trajectories. Crucially, they mask these problematic trajectories from gradient updates, so that their failures do not inject large negative signals into training. Combined with careful numeric choices, this engineering work is key to making large-scale RL feasible and stable. The authors evaluate Vision-DeepResearch on 6 challenging benchmarks, including VDR Bench, FVQA, MMSearch and MMSearch Plus, Live VQA, and Browse Comp VL. Compared to the same Qwen 3 VL backbones running a generic agentic workflow, Vision-DeepResearch delivers large gains. The 8 billion parameter version improves average accuracy by over 10 points, with especially big jumps on MMSearch and Live VQA. The 30 billion parameter model reaches an average score of about 56.9, improving its backbone by 16 points. These results show that the new data and training paradigm meaningfully upgrades deep research behavior beyond what prompting alone can achieve. Vision-DeepResearch is also compared against other multimodal deep research models like MMSearch R1 and WebWatcher, as well as proprietary systems such as GPT-5, Gemini 2.5, and Claude Sonnet under agentic workflows. On the reported benchmarks, Vision-DeepResearch consistently outperforms existing open multimodal deep research models and is competitive with or better than strong closed-source agents, despite using fewer parameters in some cases. This suggests that carefully designed trajectories, fuzzy VQA synthesis, and long-horizon RL can close much of the gap to large proprietary systems. The ablation studies clarify which components matter most. Without any retrieval, performance collapses, confirming that external evidence is essential. Adding whole image visual search gives only modest gains, and can even hurt on some benchmarks, because full image queries are easily distracted by background clutter. Introducing multi-scale cropping for visual search dramatically improves performance on tasks that depend on precise visual grounding. But the best and most balanced results come from combining cropped image search with text search. Crops provide clean visual anchors, while text search supplies the long-tail factual knowledge that images alone cannot reveal. Another ablation looks at the impact of different training data and methods. Starting from the base Qwen3 VL model, adding verified VQA trajectories with tools already brings a big jump in performance. Adding text-only QA trajectories shows that the vision-to-text bridging pipeline successfully transfers deep research skills from text to multimodal tasks. Incorporating fuzzy multi-hop VQA trajectories yields further improvements, especially on multi-hop benchmarks. Finally, reinforcement learning on top of all this supervised data produces the best overall results, confirming that online interaction is crucial for refining long-horizon decision-making. The RL training curves reveal how the agent's behavior evolves. At the beginning, the model tends to produce long trajectories, calling tools many times without much focus. As training progresses, it learns to use tools more strategically. Average trajectory length decreases, while the reward, meaning answer accuracy, increases. This indicates that the agent is learning when it has gathered enough evidence and can safely stop searching, rather than blindly exploring until it hits hard limits on turns or context length. A concrete example illustrates how Vision-DeepResearch behaves. Given an image from a lecture at an Ivy League university and a question about the lecture date, the agent does not guess immediately. Instead, it goes through many rounds of cropping and search, first exploring noisy or irrelevant regions, then gradually focusing on key entities like the speaker's name and institutional affiliations. It verifies that the institution is in the Ivy League, then uses that information to refine text searches. After more than 20 rounds, it finally retrieves a page that clearly states the lecture date and confidently outputs the correct answer. Despite its strong results, Vision-DeepResearch has clear limitations. It depends heavily on external search engines and the current state of the web, so performance can vary with search quality and page availability. The reinforcement learning phase is constrained by API costs and time, so the authors could not fully scale up training, and they expect further gains with more extensive RL. Finally, the work is centered on factual visual question answering. Extending the same deep research paradigm to other multimodal tasks, such as interactive web navigation or complex planning, is an important direction for future research. To wrap up, Vision-DeepResearch shows that multimodal agents become much more capable when we stop treating search as a single shot and instead embrace iterative, multi-scale, multi-entity exploration. By carefully bridging visual evidence into text-only deep research models, the system inherits strong, long-horizon reasoning skills. And by combining rich, automatically synthesized trajectories with reinforcement learning in a real online environment, the model learns when and how to search and when to stop. This work points toward a future where multimodal agents can truly perform deep research across both images and text.